Hello, everyone, and thank you for joining us for our presentation on MPC Research Project 597. It is removal of E. coli from stormwater. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 9 universities in Colorado, Montana, North Dakota, South and Wyoming. Thank you to the MPC for providing resources for this opportunity to deliver the research and presentations like this. We certainly appreciate your participation as well. Our speaker today is Dr. Guang Wei Hua. He's currently an associate professor in the Department of Civil and Environmental Engineering at South Dakota State University. He received his PhD degree in civil engineering from the University of Massachusetts at Amherst. Prior to joining SDSU, he had 6 years of consulting experience in water and wastewater treatment. His current research interests include drinking water treatment, disinfection byproducts, and stormwater treatment. With that, Dr. Hua, I'll turn it over to you.
Thank you, Chris, for the introduction. Good morning, everyone. Today, I'm going to talk about a research project that I have been doing at SDSU about removal of E. coli from stormwater. And these projects have been funded by MPC and the local communities. So first, I would like to talk about some background information about the stormwater. We know that stormwater is a result of rain or snow melt flowing over impervious surfaces such as road, street, and parking lot. And we know that if we have impervious area, that will increase stormwater runoff. Under natural conditions, about 10% of the precipitation becomes runoff. And under urban conditions, that has a lot of impervious surfaces, and about 50% of precipitation becomes runoff. So therefore, stormwater management has been a major concern for urban areas. And as we continue to expand urbanization, we need to properly manage stormwater runoff in order to reduce the flood risks and other concerns. And in addition to the stormwater quantity, stormwater quality is also another major concern. Because when the stormwater runoff flows through the surfaces, the runoff can carry a large amount of contaminant. Here I have several major lists of the potential contaminants resulting from stormwater runoff, including nutrients such as nitrate and phosphate, organic chemicals, oil and grease, heavy metals, primarily copper and zinc, and some suspended solids such as sand and other particles. And also, stormwater can also carry microorganisms such as virus, bacteria, and others. And in order to manage stormwater runoff, cities, and municipalities have developed many tools that can control stormwater runoff. Here I have several major examples. The first one is a detention basin. Detention basin is a dry pond. Basically, that basin will temporarily hold runoff and release over a designated time period, such that we can reduce the flooding risk when the storm event occurs. So the second example is called a retention basin. Retention basin is a wet pond, and the retention basin will have a permanent pool of water, and the water will be reduced through evaporation and infiltration. And certain on the flood event, the water can also be discharged through a controlled discharge weir. And these two tools are mainly used to control the stormwater volume, and it can also remove some of the sediment, such as suspended particles. And the third example of the stormwater best management practice is infiltration basin. Basically, for those type basins, we will add some media to allow the water to diffuse into the groundwater. So basically, the stormwater will be directly discharged to groundwater, such that we can reduce the surface runoff volume. And this type of basin can also remove sediment. The fourth major type of practice is called the bioretention cell. And this cell has a mixture of soil and plants, and also the stormwater will infiltrate from the cell to the ground. And because we can use plants in the cells, those plants can remove organics and some of the nutrients. And for this project, our focus is E. coli. And because many of the current best practices are not effective at remove bacteria such as E. coli. So this is the focus of this project. And E. coli is widely used as an indicator of fecal contamination. And if there are any fecal contamination, E. coli can indicate the presence of those contaminants. And E. coli is a group of gram-negative bacterium, and they are rod-shaped. So actually, most of the type of E. coli are harmless. They don't cause health problems. But however, certain types of E. coli, such as E. coli O157H7, can produce a powerful toxin. So if people consume those E. coli contaminated water, some symptoms can develop, such as diarrhea, vomiting, and fever. So that's why E. coli is a major concern in surface water quality. And in order to regulate bacterial contamination in surface waters, EPA developed national recommended recreational water quality criteria. And based on the estimated illness rate, if the regulation is for 36 illness rate per 1,000 people, the 50th percentile is 126 per ml. So if you want to reduce the illness rate to 32 per 1,000, and the E. coli concentration for 50th percentile should be 100 per ml. And these regulations have been widely adopted by state regulators to control the water quality in surface water, such as lakes, rivers, and others. Here in South Dakota DENR published a statewide integrated report for surface water quality every year. In 2022, based on the survey of surface waters in the state, and we found out that about 78% of the assessed stream miles did not support one or more assigned beneficial uses. So basically, we have a large portion of the surface waters that do not meet one or more beneficial use designations. And the most important contaminant in South Dakota, total suspended solid, basically sediment and bacteria such E. coli. And in eastern part of South Dakota, where SDSU is located, we have a major river called the Big Sioux River. And Big Sioux River plays a major role in the economic development and agriculture production in eastern South Dakota. And based on the monitoring results, E. coli is the major contaminant that can cause the impairment in Big Sioux River. And the urban stormwater runoff from highways, streets, parking lots, and other areas can be a significant source of E. coli. And based on our testing results, some of the E. coli concentration in urban runoff can reach more than 10,000 per 100 ml. Just to recall that the EPA regulations for recreational water use, the area should be less than 126 or 100 per 100 ml. And in order to remove a different contaminant from surface or surface runoff, and the media filtration has been developed as the treatment tool to address some of the contaminant issues. And in this type of media filtration technology, we use a permeable reactive material to intercept and treat stormwater runoff. And these technologies are considered low cost and low maintenance for stormwater treatment. And the selection of the material are the most important part of the design and the development of the technology. And those media and the material will be selected to remove nutrient, heavy metals, bacteria, organics, and others. And there are many materials that have been tested in laboratory scale experiment, such as zeolite, calcite, limestone, natural minerals, iron products, steel slags, the industrial recycled material, and others include wood chips, tire crumbles, biochar, drinking water treatment residues. So these and many others. And most study on media filtration has been in the lab scale, and generally there's a lacking of pilot and full-scale applications of media filtration for stormwater treatment. Here I have two examples for media filtration technology to address stormwater quality issues. The first one is a steel slag filter. And this filter is installed at Stillwater Country Club in Oklahoma. And this technology is developed by Oklahoma State University. And when the runoff flows through the steel slag filter, nutrients such as phosphorus can be absorbed by the steel slag. And the other example is called iron sand filter. And this technology is developed by University of Minnesota. And I have one example of installation example at the Prairie Lake, Minnesota. So basically, iron and sand will mixed and installed in the filtration channel. And when the runoff flows through the channel, phosphate will be removed by the iron sand filtration. So these are the two examples can give you an idea how the field installation would look like for media filtration for stormwater treatment. And for this project, we focus on two recycled material. The first one is called recycled steel chips. And the reason why we select recycled steel chips for two reasons. The first one is that they are low cost and readily available for stormwater treatment. And the second reason is that when these steel chips oxidize, they can form iron oxide on the surface. And iron oxide are the material that we are using for stormwater treatment. And the second group of material that we are using for this project is called steel slag. Steel slag is a byproduct of steel making, and it contains also iron oxide and magnesium oxide. And they are produced during the separation of the molten steel from impurities. So basically, they are the impurity from steel making. And this material has been used for transportation agencies for road construction. They are very good material, alternative material for road construction. And we found out from other studies that steel slag also has a very good absorption capacity for phosphate. So these are two materials that we focused on during the development of media filtration for this project. So these are the project objectives for this study. So first, we want to develop a low maintenance, low cost media filtration system for stormwater treatment. Specifically, we are using recycled steel byproduct, including steel chips and steel slag. And the treatment goal of this filter media technology is to remove E. coli from stormwater runoff. And also, in addition to lab studies, we want to perform a field study to determine the long-term performance and the application potentials of this technology for real stormwater treatment. So these are the three objectives for this project. And we divide this project into three phases. The phase 1 and the phase 2 are lab scale, and we conduct batch adsorption studies to evaluate different material for E. coli removal. And through the batch study, we were able to identify the most efficient materials for E. coli adsorption. Following batch adsorption study, we conduct a column study on the continuously flow conditions. And we select those materials that identified from batch study for the column study. So after we complete the batch and the column studies, we identify a field study site at the city of Brookings in South Dakota. And we installed a field scale filter, and we determined the long-term performance of the field scale filter over 3 years of period to evaluate E. coli removal under field conditions. So these are the three phases of this project, and I'm going to present the results based on the three phases. So during the batch experiment study, we selected 4 materials, including limestone and zeolite. These are the 2 natural materials that are readily available. And these 2 materials have been evaluated as stormwater treatment material, filtration material for phosphate removal. And we want to know whether these 2 materials can also remove E. coli or not. In addition, we select 2 recycled steel byproduct, steel chips, and we collect material from 2 recycling companies, one located in Sioux Falls, South Dakota, and the other one is located in Marshall, Minnesota. So we collect recycled steel chips from 2 locations. And also we collected steel slag from a steel making company, New Cooperation in Nebraska. And this is a batch study design. First, we select the adsorption material, and we use the sieving to collect the material that are in 1 to 2 millimeter range. And following that, we create simulated E. coli solutions. So basically, we grow the E. coli media in the lab, and then we dilute the E. coli culture into different concentrations from 10 to 10 to the 4 per milliliter. And we conduct a batch adsorption experiment under different temperatures from 5 to 30 degrees Celsius and 3 pH values, 5, 7, 9, to cover a wide range of real stormwater conditions. And we performed the batch adsorption experiment from 2 to 24 hours to evaluate the impact of different contact times on the E. coli adsorption. So after different batch adsorption experiment, we analyzed E. coli concentration after the treatment. Then we compared with initial concentration to evaluate the removal efficiency. So these are the experimental equipment we used for the batch adsorption study. We use a temperature controlled shaker to conduct the batch experiment. And we use a centrifuge to isolate the E. coli culture such that we can prepare the diluted solution for our experiment. And we use IDEX and the sample sealer to determine the E. coli concentration before and after the treatment. So this figure shows the result of the adsorption capacity of the four materials, steel chips, steel slag, zeolite, and the limestone, and over 24-hour adsorption period. And based on this result, we learned that E. coli adsorption to the filter media are a fast process. And based on our results, more than 80% of the 24-hour adsorption capacity can be completed within 6 hours. So we observed fast kinetics for the four material. And in addition, we found that the adsorption capacity of steel chips are almost more than 1,000 times of the other material. So we had to divide the steel chip result by 1,000 in order to put all the data points into one scale. So therefore, steel chips are much more effective compared to other materials. And also we found out that steel slag are better absorbent materials than zeolite and the limestone, which are natural minerals. So this is the result we found based on the first set of batch adsorption study. And also we evaluate the impact of different influent E. coli concentrations on the adsorption capacity, on the adsorption efficiency of the four materials. For steel chips, and over a wide range of influent concentrations, the removal efficiency did not vary by that much. It varied from 89.5 to 92.7 range. So we were able to achieve very good removal efficiency over a wide range of influent concentrations. And we found that the influent concentration had a larger impact on steel slag, limestone, and zeolite. And also, we found a similar removal efficiency order as the kinetic study. So overall, based on the E. coli removal at different concentrations, we conclude that steel chips are much more efficient than steel slag, which is more efficient than limestone and zeolite. And for temperature impact, and based on our result for steel chips and steel slag, and we learned that for 20 degrees C and 30 degrees C, the difference are minor, and we were able to maintain good removal for the two temperatures. However, when the temperature dropped to 5 degrees C, the removal efficiency substantially reduced. So therefore, we expect that during early spring runoff, when the stormwater runoff temperature is close to the freezing point, we expect the removal efficiency will be reduced. This is likely because the mobility of E. coli under low temperatures will become much less compared to normal stormwater runoff temperatures. And we also look at the pH impact. We know that the stormwater runoff pH can vary based on the road conditions and seasonal variations. And based on our batch adsorption study, we learned that acidic pH can help the removal of E. coli. However, the difference between pH 5 and the neutral pH are minor. We achieve good removal for the two pH values. However, at high pH values, the removal efficiency substantially reduced. So basically, we learned that under acidic conditions, steel chips and steel slag had a better performance compared to alkaline pH conditions. And this is the summary based on the batch experiment. First, perhaps the most important is that we identify that steel chips are much more efficient than steel slag for E. coli removal, and the steel slag was better than limestone and zeolite. So this is the order of the removal efficiency among the 4 tested materials. And also steel chips exhibited at least 1,000 times higher E. coli adsorption capacity than other materials. And also environmental condition can impact E. coli adsorption, and the adsorption typically increases with increasing temperature, but decrease with decreasing pH values. So after the batch study, we identified steel chips are the most efficient E. coli adsorbing material, followed by steel slags. So therefore, we decided to perform additional column study to evaluate the removal efficiency of steel chips under continuously flow conditions, because the column experiment conditions is more closer to the real stormwater filter treatment conditions as we continue push the water through the filter medium. So this is the setup for the column study. We have a glass tank that holds the influent, simulated stormwater runoff that has different E. coli concentrations. And we use a peristaltic pump to pump the influent through the column that contains steel chip media. And we measured the influent and effluent concentrations to determine the removal efficiency during continued flow conditions. So once again, these are the materials that were used for column study, and we sieved the material into different sizes. 0.5 is considered fine material, 1 to 2, 2 to 4, and 4 to 8 millimeter. And the 4 to 8 millimeter size is considered coarse material. And we evaluate the effluent concentration divided by influent concentration over 72-hour operating time. So here, on the y-axis here, C means the effluent concentration, and C0 means the influent concentration. So basically, the y-axis indicates the fraction of the effluent concentration against influent concentration. We look at the size impact, different sizes of material on E. coli removal. And we learned that as the size becomes bigger, the removal efficiency gradually declines. For example, for the fine size particles, 0.5 milliliter to 1 millimeter, we were able to achieve constantly about 99% removal. And as the size increases, we found that the removal efficiency gradually declined to about 58% for the highest size material, which is 4 to 8 millimeters. And also we learned the removal efficiency were very stable over 72-hour period, even though there are some early breakthrough between 0 and 6 hours. But after 6 hours, we were able to maintain very stable removal. And the removal efficiency did not decline between 12 and 72 hours. So therefore, this result is important, and this can indicate that steel chips are able to maintain stable removal over a long period up to 72 hours.
Dr. Hua?
Yes.
So just to check the understanding, are the percent removal stats showing the percent of the total coliform loading or the percent of the 24-hour removal?
The removal percentage indicate how much being removed by the steel chips. For example, if the influent concentration is 100 per ml and 99% remove, that we only have 1 in the effluent.
Okay, thank you.
And the y-axis indicates effluent concentration percentage. So 100 minus the y-axis is the removal efficiency. So here we also look at the impact of contact time on the removal of E. coli through the column study. Once again, the y-axis indicates the ratio between the effluent to the influent. And I put the removal numbers for each of the line for easy understanding. And we evaluate 3 contact times. EBCT means empty bed contact time. That's the travel time of water through the filter column. And we evaluated 5 minutes, 10 minutes, and 20 minutes. And based on our results, we observed that when the EBCT or contact time is 5 minutes, we were able to maintain 87% removal over 72 hours. And when we increase the contact time to 10 minutes, we were able to achieve, I think, roughly 90% removal. And when we further increase the contact time to 20 minutes, then we were able to achieve 98% removal. Overall, for a wide range contact time, 5 to 20 minutes, we were able to achieve all very good removal efficiencies. So that means this filter technology can be adopted to different stormwater event that has a different flow volume, which will result in different filter contact times. And also, in order to confirm the pH impact from the batch study, we also compared the pH values impact on the E. coli adsorption efficiency. We did observe that the pH acidic environment favored E. coli removal. So at pH 5, we were able to achieve 95% removal. And at pH 7, the removal efficiency reduced to 90%. And we observed some interesting results at pH 9. If you recall, during the batch study, pH 9 has the lowest removal efficiency. We did observe the lowest removal efficiency at early stage of the column operation at 87%. However, as we continue to increase the detention operating time, the removal efficiency gradually increased to 92%. And we attributed this phenomena to the ferrous coagulation impact. We observed that some of the dissolved iron were able to coagulate E. coli and to form a deposit. That's what we observed from the column study. So basically, in addition to the filtration and adsorption impact, we found at high pH values, the dissolved Fe is able to coagulate and form flux that could be trap E. coli from the water. Organic matter is another competitor for E. coli adsorption because when the stormwater travels through the surface, they can pick up some of the organic compound, and we call those compound as natural organic matter. And we want to know whether those organics present in the stormwater runoff can impact E. coli removal or not. And indeed, this figure shows the attached E. coli against the different natural organic matter concentrations. So the blue circles indicate there are no natural organic matter. Then we added 5 milligram per organics into the influent concentration as indicated the yellow triangle. And also we increased the organic matter concentration to 30 milligram per liter as indicated by the green triangles. And we found that as we increase the concentration of organics, the E. coli adsorption efficiency declined. And the percent decline is 25 for 5 milligram per liter and 50% for 30 milligram per liter. So therefore, if the stormwater has high concentrations of organics, it may reduce the E. coli removal efficiency. And this figure shows the E. coli removal mechanism, how steel chips remove E. coli from stormwater runoff, and why pH and organic matter can have impact on E. coli removal. And we know that E. coli in aqueous solutions has some charge on the surface. Typically, E. coli species has a negative charge on the surface. And we know that steel chip surfaces has a lot of iron oxide. Iron oxide are positively charged. So because the charge on the E. coli and the steel chip surface are opposite, so they tend to attract each other through electrical static attraction. So that's the reason why steel chips are very efficient for E. coli removal. And under high pH conditions, we have a high concentration of OH hydroxide, which is OH minus, negatively charged. And those OH ions will compete for the adsorption site. So therefore, we have high removal under low pH conditions. Similarly, many organic compounds are also negatively charged. They can compete to the adsorption site. So this can explain the observed impact of pH and organic matter on E. coli removal by steel chips. And in order to verify our hypothesis, we performed some microscopic scanning using SEM technology, scanning electron microscopy to look at the steel chip surface before and after the treatment. So the figure A shows the steel chip surface before the experiment. As you can see, there are lots of crystal forms on the surface. Those are the iron oxide formed by iron and oxygen. And after treatment, we found a high density of rod type of bacteria. So therefore, we verified E. coli bacteria can be effectively attached to the steel surface. So this is a summary from our column study. Steel chip column maintained steady E. coli removal up to 72 hours. So we were able to maintain steady removal over a long period. And also environmental factors could affect E. coli removal. And the column exhibited better E. coli adsorption under small sizes, long contact time, and low pH levels. And also the organic matter present in the runoff can negatively affect E. coli adsorption. So with the success of batch and column studies, we identify steel chips as the most effective material. So therefore, we want to test those materials under field conditions to verify their performance and promote full-scale applications. So we identified a stormwater runoff site at the city of Brookings. So for those who do not know where city of Brookings is, so basically Brookings is located at eastern South Dakota. It's about 60 miles north of Sioux Falls. And through working with the city, we identify a residential detention pond as the field studies site. And that detention pond has about 16-acre drainage basin. The yellow circle shows the inlet of the detention pond. That's where we placed our field scale filter. And the yellow arrow shows a drainage pipe underneath the ground, which will carry the runoff from the street and the neighborhood to the detention pond. And the photo shows the residential detention pond, and the inlet is located at the left upper corner from this photo. And we collect the two material for this study, and we use the steel chips as a major filter media for E. coli removal. We also collect steel slag as a supporter media to support the performance of the steel chips. And also steel slag can also improve the E. coli removal because they are also efficient compared to a natural mineral such as zeolite and limestone based on our batch study. And we collect steel slag from Nucor Steel, Norfolk, Nebraska. And we process the material into two sizes, a large and a small, which are in 4 to 94 millimeter and 2 to 4 millimeter respectively. And for steel chips, we collect from a recycling company in Marshall, Minnesota. And also we process the material to the same size range as the steel slag. And this figure shows the construction of the field scale filter. We use a steel structure to contain the filter media. And the steel structure has a height of 8 inches, length of 6 feet, and a width of 5 feet. And during the storm runoff treatment, we measure the flow and compare the porosity of the media. We determined that the retention time was somewhere between 13 to 50 seconds. And these two photos shows how our graduate research assistant, graduate student, installed the filter media. So basically, we place the structure at the inlet of the detention pond, and then we mixed steel slag and steel chips and added uniformly, and then we added to the steel structure. And these two photos show the treatment of the stormwater runoff on the real storm event. So basically the water will flow through the pipe and then through the filter media. And we collected sample from the inlet and the outlet to compare the treatment performance for various storm events. And these are the media conditions for the 3 years study. In 2018, we used 70% steel chips and 30% steel slag. In 2019 to 2020, we used 50% steel chips and 50% steel slag. So the total study period was 3 years. And this figure shows the E. coli removal, the E. coli in the influent and effluent of the steel filter over different stormwater events. We conducted experiment for 4 events, and also we collect sample at the different storm times. And on average, we found that the steel byproduct filter removed about 50% of the influent E. coli in 2018. Similarly, in 2019, we also evaluated 4 storm events, and the average E. coli removal was 53%. And also one thing I want to point out here that we found out in this detention pond, the influent E. coli concentration varies. Like, for example, in 2019, the influent concentration varied from about 1,000 to over 16,000 per 100 ml. So we found a large amount E. coli in this detention pond, and we were able to remove about 50% through the filter media. In 2020, very similar removal, even though the field has been in the field for 3 years, we were able to achieve very similar removal after 3 years. And the average E. coli removal was again about 50% in 2020. So in addition to E. coli, we also monitored phosphate removal. So based on our past study, we know that steel chip and steel slag are very good material for nutrient phosphate removal. And here we monitored the phosphate removal in 2020. We found that the average percentage removal was 51%. So we were able to achieve not only E. coli removal, but also we were able to remove phosphate. So therefore, this filter technology using steel chips and steel slag were able to remove multiple contaminants from the stormwater runoff. So these are conclusions from our batch, column, and field scale study. So first, steel chips showed much higher E. coli removal capacity than steel slag, limestone, and zeolite. Steel chips, steel slag filter removed about 50% of the E. coli and about 50% of the phosphate during the 3-year field study at City of Brookings. And overall, we conclude that recycled steel byproducts are efficient filter materials for E. coli and phosphate removal from stormwater runoff. And this project was funded by several sources, US DOT Mountain Plains Consortium, and we have local support from East Dakota Water Development District and James River Water Development District, and also City of Brookings helped us to identify the field study location and helped us with filter installation. So we would like to thank the funding agencies and the City of Brookings for their assistance for this project. And the principal investigator for this project include myself, Dr. Christopher Schmidt, and Dr. Kyung-Lan Min at SDSU. And we graduated 4 master students through this project, including Guyan, Peng, Jason, and Brandon. So this is the ongoing project to apply this technology in full-scale applications. So we received additional funding from MPC, East Dakota Water Development District, and the City of Sioux Falls. So we will install a large pilot-scale filter at a stormwater site in the City of Sioux Falls. So we plan to continue to apply this technology in real stormwater treatment conditions and to remove E. coli from stormwater runoff and to improve the surface water quality. So this completes my presentation today. Thank you very, very much and appreciate your time. And if you have any questions, feel free to ask.
Thank you, Dr. Hua. If you guys could please, if you have any questions, go ahead and put those in the chat or unmute yourself and ask your question or questions. Is there a timeline on how long the media lasts before it needs to be replaced or refreshed?
This is a very good question. For our field study, and our filter lasts at least 3 years with very minimal maintenance. So therefore, we think this technology can be applied in the field for a very long time. Certainly, we need to look at the longevity of the material. And regarding steel chips, we believe that if we have water and oxygen, the steel surface will be continuously oxidized, and the capacity will be continually regenerated. So therefore, we believe it will last at least 3 years and perhaps much longer. And we will observe our full-scale application at Sioux Falls to evaluate how long it can last on the large application scales.
Okay. And then what concerns are there regarding loss of media that gets into the ecosystem?
For the media filtration technology, we would want to contain the media into a structure. Therefore, we typically utilize large particle sizes such that they are not easily washed out. And also in the field design, we can put some containment like the weir or other design to hold the media. Certainly, there may be some loss of dissolved species, such as the dissolved iron and other very fine particles. But we measure dissolved iron concentrations. Those concentration level are not concerned based on our experiment. Certainly, we will continue to monitor the leached dissolved species from continued study to make sure that when we remove contaminant, we don't generate unintended consequences that could harm the environment.
Okay. And since E. coli can survive several weeks in water, how quickly does it perish in the filter?
This is a very good question. We know that the stormwater runoff will come and go, and if you look at the photo of the SEM, we observe a large density of the E. coli being attached on a steel media, and we think that the E. coli will be attached to the media during storm runoff event, and during dry time period, so the E. coli would die off and be ready, so the media will be ready for the next storm event. Certainly, we do plan to collect some material to look at the intermediate dry and wet cycles to see how long E. coli can survive on the media. But we believe that during dry period, they would die off.
Okay. And then to kind of go back to that first question about how long the media lasts, is there a plan or concern with disposing the media that has lived its lifespan?
Yes, regarding the media replacement, first of all, we were able to maintain at least 3 years of treatment. And those materials are low cost and readily available at the recycling materials. So therefore, the replacement cost will be very minimal. So even the media needs replacement every several years. So the cost is not a major concern based on our understanding. Regarding the disposal, those materials can be easily disposed by landfill or some beneficial applications. For example, we learned that steel slag and steel chips can absorb phosphate. And phosphate can be used as a nutrient source for agriculture production. And steel slag has been used in road construction. They are considered environmental safe. So we believe those materials can be reapplied for environmental applications such as road construction, a soil conditioner, and other conditions. And we are continuing to evaluate potential beneficial reuse of those materials.
That makes sense. I was actually told once upon a time ago, this is a side story, but I was told by somebody that if you had some old nails, they said to bury them with your evergreens because of the nutrients that are discharged through the nails. It actually feeds the evergreens. And I never believed if that was true or not, but this could be a case where maybe it is possibly true.
Actually, you're right. Iron is an enhancer for lawn, for grass, and for many material. So certainly, a large amount of iron may not be a good idea, but some iron enhancement can improve the land plants growth. Yeah.
Thank you for attending today's TLN event. We certainly appreciate your time, participation, and attention. And Dr. Guang Wei Hua, we certainly appreciate you sharing your research, and good luck with your additional research with completing this project. We certainly wish you the best with that. I sincerely hope everyone enjoyed and gained some new knowledge from today's session, and I encourage you to visit our website at translearning.org for upcoming learning opportunities, as well as to access the learning management system. And if you see a topic out there that is of interest to you or your peers, please do share that with them so they have the opportunity to attend some of these wonderful sessions as well. With that being said, have a fantastic rest of your week, and don't forget to be awesome. Take care, everyone.